Hello and welcome to the video lecture on chemistry of carbohydrates. This is the study material 5. Here we will discuss a few reactions of our carbohydrates. Specifically, we will concentrate upon the chain ascension and chain degradation. That means we want to increase the carbon chain of any carbohydrate or monosaccharide by 1 carbon unit. That is called chain ascension. And if the reverse reaction is possible, that we can reduce the carbon chain by 1 carbon unit, then that's chain degradation. In chain ascension, we have the famous Kiliani-Fischer synthesis. Way back in 1885, Heinrich Kiliani was the one who first reported that if you take an aldose and you react that thing with sodium cyanide, cyanohydrin formation takes place, which is a typical reaction of aldehydes. So you can introduce a carbon nucleophile onto the electrophilic aldehyde group, and the cyanohydrin can be consequently hydrolyzed into a corresponding carboxylic acid, which is the aldonic acid in case of aldoses. Later, Fischer converted those aldonic acids into their lactones, and as we know that the method of the reduction of lactones into the corresponding aldehydes were well established at that point of time. This gave the route to conversion of one aldose with n number of carbon atoms to a higher aldose with n plus 1 number of carbon atoms, where the additional carbon was supplied by cyanide, which eventually became the aldehyde. And because you have started from this CHO, and this is the, suppose in your starting aldose this was the C1 carbon, but in your addition reaction of cyanide this will become the C2 of the cyanohydrin molecule, and because you have a CHO group adjacent to a chiral center, this aldehyde has two diastereotopic phases, and those two diastereotopic phases will afford a mixture of stereoisomers at C2. And this reaction sequence will eventually generate two aldoses with n plus 1 number of carbon atoms, which will be epimeric at the C2 carbon. So the Kiliani-Fischer ascension was extremely vital in terms of stereochemistry, because the stereochemistry of the chiral centers or asymmetric centers of the original aldose remained unaffected, but the stereochemistry of the new center, which was the C1, which was the sp2 hybridized CHO, will now become stereogenic, and on that carbon we will get an H and a OH, and we will get both stereoisomers, both diastereoisomers. So this synthesis actually gives you the freedom to generate the next higher pair of aldoses, which are epimeric at C2. An example is, obviously you can take the example of D-arabinose, and we know that D-arabinose has the same configuration at its C2, C3 and C4 to that of the configurations of C3, C4 and C5 of both D-glucose and D-mannose, which are epimeric at the C2 position. So a Kiliani-Fischer synthesis of D-arabinose is expected to give a mixture of D-glucose and D-mannose. So let's put that theory into test. If you treat this thing with aqueous sodium cyanide, then cyanohydrin formation takes place. This CHO, again it has two diastereotopic phases. Cyanide can add from the one side and from the other side, but in unequal amounts, but it will eventually lead to the mixture of epimeric cyanohydrins, which are epimeric at the C2 position. That C2 was actually the C1 of arabinose, and the C1 of the cyanohydrins that was supplied by the cyanide group. Now you can hydrolyze them with an alkali solution, then acidification, and then you separate the epimeric aldonic acids, because cyanides under alkaline condition will be hydrolyzed to the corresponding carboxylate salts, Acidification will give you the corresponding carboxylic acids, and if you have CH2H here and if you have carboxylic acid here, then those are the aldonic acids. So basically you are going to get a mixture of D-gluconic acid and D-malonic acid from the D-gluconitrile and D-malonitrile mixture, and at this stage you have to separate them. So the D-gluconic acid and the D-malonic acid, they are separated. If you heat them, then they will form the alpha, beta, gamma lactone, where the C4OH will form the lactone with the carboxylic acid. So you get D-gluconolactone and you also get D-manolactone, but these are already have been separated. Now you have to reduce these lactone groups into CHO by carefully controlling the pH under 3 to 4, because if you increase the pH above 5, then these things will be completely reduced into CH2H, and in that case you will end up with glucitol and mannitol. That's what you don't want. You want these things to be stopped at the aldehyde stage, so you control the pH at 3 to 4. So the C1 lactone will gets converted to CHO, and we get D-glucose from the D-gluconolactone and D-mannose from the D-manolactone. So obviously the carbons that were numbered 1, 2, 3, 4 and 5 in D-arabinose are now numbered 2, 3, 4, 5 and 6. The configuration at the 2, 3, 4 of arabinose is same as that of the 3, 4, 5 of both the products, but the new stereocenter that is being generated at the C1 of arabinose, it has OH on one side on one molecule on the right side and OH on the left side on the other molecule. So these two are the two aldohexoses which are epimeric at the C2 position. So this is in essence the Kiliani-Fischer synthesis, and you can go for the conversion of aldotetrose to aldopentoses. If you start from aldotetrose, you will get two aldopentoses which are epimeric, which will be epimeric at their C2. There is a name reaction which converts the cyanides directly into CHO, which is the Rosenman reduction. That is done with hydrogen in aqueous medium in the presence of palladium barium sulfate under high pressure and maintaining the pH at slightly acidic condition. So you can also adopt for that. So the hydrolysis followed by acidification, you may not go that way. You may go for the Rosenman reduction of cyanide to CHO, but the underlying theme of this conversion remains the same. So you get higher aldoses which are epimeric at C2. So this is for the chain ascension thing. At least for now we will only consider this one, but later on we will see other chain ascension techniques as well. Now if you want to do the reverse reaction, so if you want to decrease the carbon number by say 1 carbon unit, you can also do that, and those reactions are known as the degradation. In these cases we will consider two reactions which are Wohl degradation and the Ruff degradation. Both these reactions will if you start from an aldohexose, then this CHO group will somehow be made into something which will leave, and this C2OH will be converted into CHO. That means that the C2 will lose its stereochemistry, and the carbon that was C2 in your starting aldohexose will become C1 CHO in your aldopentose product. So that means that from C2 onwards, in case of any aldohexose, any stereoisomers, any stereochemistry or configurations that you have here is preserved, and that also means that the stereochemistry of these three carbons in case of an aldohexose will be replicated in the stereochemistry of these three carbons in the product aldopentose, which also implies that you can start from C2 epimeric aldohexoses like glucose and mannose, knock out the CHO in both cases, convert the CHOH functionality at C2 into CHO in both cases, and then you will end up with the same aldopentose which has the same configuration at its C2, C3 and C4 as that of the configurations of C3, C4 and C5 of our starting aldohexoses, be it D-glucose or D-mannose. So in essence it is the reverse of the Kiliani-Fischer synthesis. And the chemistry is also reversed because you introduced the additional carbon in the form of cyanide. You will remove this CHO in this case also in the form of cyanide. And so thematically, Wohl degradation, where two C2 epimeric aldohexoses can be converted into the same aldopentose, or two C2 epimeric aldopentoses can be converted to the same aldotetrose. It is basically the reverse of the Kiliani-Fischer synthesis. So how do you do it? The way to do it is to first convert this glucose or mannose, whatever you have taken, which are C2 epimeric, convert them into their corresponding oximes. That can be done in presence of optimum pH and using hydroxylamine hydrochloride. So this is an oxime formation reaction via addition elimination pathway. Then you do the acetylation. Basically, you are protecting these hydroxyl groups, all 5 hydroxyl groups including the 4 secondary, and the only primary hydroxyls will be protected. So these are acetylated. And now you are converting these into the same acetic anhydride in sodium acetate reagent will also eliminate a molecule of water from this oxime and will give you the cyanide. So these things are acetylated, and this is made into cyanide. Now you can see that this is basically acetylated cyanohydrin. If you can somehow liberate a OH here, then this will become a cyanohydrin, and that cyanohydrin can be collapsed back into the parent carbonyl compound, where this will become C double bonded O and this cyanide will leave if I expose it to a base. But then the deprotection of this acetyl group or O acetyl will be required. This is done by Tollens reagent, which is a ammoniacal silver nitrate solution in presence of we have the hydroxide ion. This does two things. First of all, it hydrolyzes, or also this is also known as saponification of ester. This hydroxide will hydrolyze this OSE minus and this acetyl group in this way. That's the the BAC2 pathway that and then the liberated OH will be collapsed into the corresponding CHO in the presence of this OH minus, or you can use a secondary base such as methoxide or something like that. So these things will be hydrolyzed, everything will be like OH, 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 and these OHs are different from that one because this is a part of the cyanohydrin. So this will collapse, kick out the cyanide, and it will become the CHO, and silver cyanide will be precipitated from this reaction medium. So again, C2 epimeric aldohexoses will lead to the formation of the same aldopentose because it is the stereochemistry of the C2 which will be destroyed, but the C3, C4, C5 will remain intact and they will become the C2, C3, C4 of the aldopentose. You can do this reaction with sodium methoxide in chloroform, that is the methanolysis of acetate. In that case, the OMe minus will attack the acetyl group and liberate not acetic acid but methyl acetate. But again, the cyanohydrin will be revealed and sodium methoxide will pick up this proton, and then the carbon oxygen double bond will form and cyanide will leave, and elimination of HCN will lead to the formation of the corresponding arabenose. So that's the Ruff degradation, that's the Wohl degradation, and this is named after Alexander Wohl. Otto Ruff, he developed the other degradation process which came to be known as the Ruff degradation. Ruff degradation is converting the CHO into a carboxylate salt and then looking for a simple decarboxylation. So the philosophy is again the same. You lose the CHO and this C2 becomes the CHO in the product, and therefore the rest of the carbons configurations are replicated in the product. So again, it is the C2 epimeric aldohexoses which will lead to the same aldopentose. Just like we were generating via Kiliani-Fischer, we could generate D-glucose and D-mannose from the D-arabinose. The degradation reaction, either it will be Ruff or it will be Wohl, we start from D-glucose or D-mannose, we ultimately get the same aldopentose, that is the D-arabinose. So how do they do it? First of all, they convert this into the corresponding gluconic acids. You can do that by gluconic or mannonic acid. You can do this by bromine water oxidation, and then you have to convert it to the calcium salt, which is done by treatment with lime. And then you treat this thing with something known as the Fenton's reagent, which is a combination of 30% aqueous H2O2 in presence of a iron 2 plus salt. What happens in this reaction is, basically you have carboxylate group and you have a iron 3 plus iron 2 plus shuttle here. This iron 3 plus gets converted to iron 2 plus by accepting a one odd electron from the carboxylate, and this carboxylate will now become a radical. Okay, so this thing now becomes a radical, and iron 3 plus becomes iron 2 plus. But because H2O2 is present in the reaction medium, iron 2 plus is immediately reoxidized into iron 3 plus. So there is a shuttle which is going on. But after this has donated one electron, what will happen here? This will, decarboxylate, and via this homolytic cleavage of the C1 C2 bond, this will become now a radical. One hydrogen radical will come out of it by forming the strong carbon oxygen double bond, and this hydrogen radical will donate one electron to the iron 3 plus. So this iron 3 plus will again be reduced to the iron 2 plus, and this H dot will become H plus, and that way the iron 2 plus is constantly maintained in the reaction medium, and iron 3 plus is also constantly maintained in the reaction medium because H2O2 is present in the reaction medium. So this is the Ruff degradation. Again, from glucose and mannose, C2 epimeric aldohexoses, you get arabinose. So that's how you do it. Now we will discuss a few important transformations. One is epimerization of D plus glucose into D plus mannose. They may or may not give you this optical rotation, but what is important is to recognize that both of them are D. So basically I need an epimerization here. So you could think that epimerization, we can go for the Lobridib-Bruin-Albert von Eckenstein rearrangement, but the problem is that leads to a mixture of many different products. There could be reverse aldol reactions which lead to fragmentation. There will also be produced the fructose, which we do not want, the ketohexose that we do not want. So this epimerization is carried out in a sophisticated way. So first you oxidize with bromine water and calcium carbonate so that you get the corresponding calcium gluconate salt, gluconic acid's calcium salt. Then you acidify, so you get the gluconic acid. This gluconic acid is tautomerized or epimerized under a very mild condition with the help of pyridine. So what pyridine does is, first of all, it takes away this more acidic proton, so this becomes pyridinium, and then this magenta colored hydrogen is taken away. Obviously this equilibrium favors this carboxylate salt immensely, but there will be some dianion present in this thing, and this dianion is basically a enolate, and then it can tautomerize by picking of this proton from the corresponding pyridinium, so that in the equilibrium you have present the corresponding mannonic acid salt, and this, when acidified, will give you the D-mannonic acid. On heating, you will get the involvement of the C4OH, lactonization with the CO2H, so D-mannolactone. All that remains for you is to reduce this lactone group into the corresponding CHO by sodium amalgam and carefully maintaining the pH at 3 to 4. Don't let the pH go above 5, otherwise you will end up with mannitol. Next up is D plus glucose to D minus fructose. So that's an interesting conversion in a sense that we are trying to reduce this to CH to OH, and we are trying to oxidize this carbon to C double bonded O. So it's a sort of a redox process. So first you form the osazone. Okay, treat this thing with excess phenylhydrazine under heating conditions so that osazone is formed, and then with osazone you can access something which is known as ozone, where these C double bonded ends are hydrolyzed into corresponding C double bonded O. You can do this thing in two ways. One is to simply hydrolyze that with HCl heat, or you can deploy a more reactive carbonyl such as formaldehyde here in presence of aqueous HCl under heating condition. This reaction is basically akin to trans esterification, where you treat one ester with another alcohol. So you treat RCOOR1 with R2OH and you end up with RCOOR2 and R1H is liberated. So in this case, formaldehyde being the more electrophilic carbonyl in reference to the corresponding ozone, it will sort of strip this molecule and take away these phenyl hydrazines, and it will itself form its corresponding phenyl hydrogens, and the carbonyl groups will be revealed here. Or if you don't remember it, it's just to deploy the HCl heat. Basically, we have now managed to oxidize this carbon. All that remains is to selectively reduce this CHO, and that can be done with zinc acetic acid. Obviously, it is a chemoselective reduction, and we are not very surprised that this is getting reduced in preference to that. This is a ketocarbonyl, this is an aldehyde carbonyl. We have a 1,2 dicarbonyl situation, so the reactivity is pretty high. But CHO will always be more reactive than C double bonded O of a ketone, and therefore it is reduced to the CH2OH, and we have D minus fructose. Next up is the reverse transformation, that if I want to do the transformation of fructose to glucose, in that case we have to reduce it, and we have to oxidize that. So this is done by first of all reducing the C double bonded O. So in this case we went for the oxidation of the C2 first and then reduction of the C1, and in this case it is the reverse. We go for the reduction of the C2 with sodium borohydride. Now that will be again a diastereoselective reduction, and it will lead to formation of D-glucitol and D-mannitol, because OH in Fischer projection will, in one molecule it will be on the right hand side, in the other molecule it will be on the left hand side. So we separate the mannitol from the glucitol because we are looking to synthesize the glucose. Then we do the dilute nitric acid oxidation. Generally, dilute nitric acid oxidation should convert both these into carboxylic acids, but if you tamper the reaction condition in such a way that when only one of these CH2OH will be oxidized, then you can end up with among many other products. This is one of the product. Obviously, you will also going to end up with oxidation of this CH2OH where this CH2H is not left untouched and this CH2H is oxidized. So that's basically the diastereoisomer of whatever we have written here. So again, you have to carry out a tedious and laborious separation process, but carefully controlling the reaction condition, and by manually separating these products, you can end up with a D-gluconic acid. Now you can heat this thing. Again, the lactonization takes place from the C4OH, and you end up with the D-gluconolactone, which on sodium amalgam reduction under carefully controlled pH will give you D plus glucose. So this thing is not very easy, in a sense that you have to first of all make a separation here, you have to make a separation here, and those things are not easy, but it is doable. The last part of this lecture is conversion of a aldopentose into a corresponding ketohexose. Now that's new. If you are trying to synthesize glucose and mannose from arabinose, you go for the Kiliani-Fischer. But if they are asking you to convert arabinose into fructose, and that too without involving the corresponding glucose, because you can, now that you know that you can convert glucose into fructose, you might get cheeky and convert arabinose to glucose and then that glucose to fructose. But if they have asked you to directly convert it without involving either glucose or mannose, then you have no other option but to go for this homologation, which is known as Wolfrom homologation after Melvin Wolfrom, whose picture I have presented here. So you start from D minus arabinose. And homologation, whenever we say homologation in organic chemistry, we almost all the time, or at least sometime, a picture is invoked in our mind of Arndt-Distad homologation. So this is exactly what they are trying to do here. So you do the bromine water oxidation, calcium salt formation, and then acidification. You end up with the corresponding aldonic acid. That is, in this case, this is the arabinoic acid. Then you acetylate everything. Okay, and then you treat this thing with SOCl2. You need to acetylate, because otherwise if you treat this thing with SOCl2, then along with the carboxylic acid groups, these hydroxyl groups, the alcohol groups will also be replaced by chlorine. So it's kind of offering a protection to the hydroxyls, because we would like to keep them as they are in the product. So you do the SOCl2. Now with the free CO2H group, you get the formation of the COCl. Now you treat it with, you guessed it, excess diazomethane, because that is the reagent that we encountered when we studied undiested homologation. So first of all, there will be a nucleophilic addition elimination, so you will get a C double bonded O CH2N2, and because CH2N2 is present in excess, one of those active protons which is activated by the adjacent N2 plus and the adjacent carbonyl will be taken away, so you get a diazoketone derivative, and that should remind you of the undiested reaction. Now you protonate this. You don't want any rearrangement or anything to happen. You just want this thing to become CH2H. The most easy way of doing it is to protonate this. Once you protonate that, then this becomes CH2, CH2N2 plus. And because you have water, aqueous acid, water will make a nucleophilic attack here, because here you have the best possible living group N2 plus. We have CH2 here, and that is alpha 2 carbonyl. So this carbon is highly activated towards a nucleophilic attack. So there will be a very smooth reaction, protonation and SN2, you will get CH2OH. The only thing that remains for you to do is to hydrolyze these acetate groups, which you can do with BSE2 mechanism, deploy an alkali such as barium hydroxide. Saponification will take place, giving rise to T minus fructose. So this is the second homologation technique alongside Kiliani-Fischer that we have studied. But Wolfram's technique or Wolfram homologation is specifically for conversion of an aldose to a next higher ketose. But the Kiliani-Fischer converts an aldose into the next higher pair of aldoses which are epimeric at the C2. So this much for this lecture. I thank you for your patience, and I will be seeing you in the next one.